So I'm going to introduce the idea of Gauss's law, which is actually a rather complicated bit of mathematics, but it's important to us because it allows us to solve for the electric field in situations where there's a lot of symmetry. I'm going to start off by introducing this idea. Let's imagine, if you will, that I've got a ring of charges. So each of those blue dots is a positive charge. I don't care how big it is. It's just, 500 coulombs or something sitting there in this ring, and I'm going to try to ask what is the electric field at the very center of that ring, at that hollow dot that I've drawn there. So you can imagine you're standing at the center of this corral of charges, and the question is, what is the electric field that you're getting because of each of those guys? You can probably look at this and guess what the answer is going to be, but let's walk through it a bit. The electric field strength due to any one charge is K times Q, the size of the charge, divided by r squared, where r is the distance from the charge, and it points in a direction r hat, which is away from the charge. The electric field points away from a positive charge, and if q is negative, that means it points back toward a negative charge. In any case, the r is the same for every one of these guys because they're laid out in a circle, and I'm standing at the center of the circle. So therefore, when I start to draw the electric field lines that each one of them makes, I'm going to realize that I have an equal amount of electric field from the ones on the right side as I do from the ones on the left side, and likewise the equal amount from the ones up top as the ones on the bottom. So therefore, the total electric field that I'm going to get standing at the center should be zero. And this probably isn't a big surprise to you. If you imagine for a second that you're standing at that center and I hand you a big positive charge, you're going to be pushed just as much from one side as the other, so there's no real reason you're going to feel a shove left or right or up or down unless you slightly move off the center spot. Any slight move will change that, but right at the center it's still zero. Likewise, if it's a negative charge or if the charge is 10 times as big, it doesn't matter how big the charge is, there's not going to be a force on something sitting at the center there, and that's why the electric field there is zero. Now let's take this into 3 dimensions. This is going to be a little trickier to visualize, but hopefully the pictures I've drawn will get the job done. Imagine, if you will, that now instead of that corral of charges, I've got a racquetball or something here that I've, instead of having little points of charge, I've got blue paint that I've painted charge all over the surface, so it's evenly spread all the way around the surface of this racquetball. So all that blue there represents a sphere that has charge on the surface of it. And I'm going to say what happens if I'm standing right at the center again, and you can probably imagine that that's going to give us the same answer we had before. There's just as much push from one side as there is from the other, so therefore the electric field at the very center of this thing is zero. But a more interesting question comes about when I say, what if I move off center, move over toward one edge? And now the expectation is, well, I'm getting much, much closer to that section of charge that's on that side of this racquetball, so therefore, since I'm really close to it, it must give me a lot more electric field. If I'm a positive charge, I'm going to be pushed away from that positive charge on the surface there pretty strongly since I'm getting close to it. And that isn't a bad idea, but you have to also consider the fact that there is the other side of the ball still there. The charge on the other side is farther away, but you'll also notice there's a lot more of the far side of the ball than there is of this close part near to me. The charge on the other side is farther away, but there's a lot more of that charge, and it's just this nice little trick of vector calculus that what happens is the total amount more charge I have over there makes up for the difference that it's that much farther away, and it totally balances out. I get just as much push from all that blue on the bottom left as I do from the lesser amount of blue on the top right, and therefore the electric field at that spot that I've moved to is zero. And this is true for any spot I could have chosen inside that ball. Let me give you a different way of looking at this. This is maybe a little more intuitive though. Think about the idea that there's electric field lines. And electric field lines always start at a positive charge, end at a negative charge, or come or go from infinity. But they have to start or end somewhere, whether that's infinity or at positive or negative charges. Well, in this case, I've got a bunch of positive charges on the surface, so if I had field lines going into the sphere, they've got nowhere to end. They have no negative charge in there to end on, and therefore I can't have them. They can't go to infinity, they can't go to a negative charge. There's no place for those field lines to go, so the field lines are in some sense not allowed inside this ball. So therefore the electric field inside this sphere is everywhere zero. No matter how close I get to one of the sides, if I'm inside that sphere, the electric field is zero. This is a bit counterintuitive, but hopefully that field line argument might make it work for you. Let me take it a step further though. Instead of saying I'm moving to some spot inside the sphere, let me go ahead and move all the way outside the sphere now. And now I'm going to have field lines that start at the charges and go out to infinity, just like we did before. But now they can go to infinity, so I can have field lines out there. And in fact, what I find is the electric field out here is the same as if I had just had that charge all at the origin anyway. So the the charge that I painted all over the surface of that blue ball, if I'm outside, then it's just identical to if I'd taken all that charge and put it at a point right at the origin. So that's something we can easily calculate as just being kq over r squared for all the q that was on the surface of the ball now located at 0, 0, 0. Now, the way you have to look at this mathematically is to think of it in terms of something called the flux. And this is a tricky thought. It's probably going to take a few times explaining it to you to get it down pat. But the idea is if I have some area there, think of this as being like a screen door or something like that, and something can, in fluid terms, we talk about flowing through. In this case, we don't really have something flowing, but there's electric field lines that can point through that, if you will. So I could have an electric field, and this is a certain amount of area that intercepts that electric field and has it pass through. Now, notice I've drawn this off at an angle. It's not going straight through. So the flux is actually defined, not quite precisely, but a definition for us is that it's the electric field times the size of the area times the cosine of the angle between them. So let's think about this a second. The stronger the field is, the greater the flux is going to be. If I have a bigger electric field, I'm going to get more flux. If I have a bigger area, I'm going to get more flux. I'm sort of capturing more of the field as it passes through. And then that theta, what that does for me is if theta goes to 0, if the field is lined up so that it goes straight through the area, then I'm going to have a greater flux. If the field is tilted over a long way, the flux is less, if cosine of 90 goes to 0, of course. So the reason this is important to us is because it gets to Gauss's law, and the precise definition of Gauss's law here is that the flux, what we're going to label with a capital phi, E times A times cosine theta, must be equal to the charge that's inside a closed surface divided by epsilon naught. We introduced epsilon naught back when we talked about Coulomb's law a few days ago, and I'll show you why we're using it here in just a minute. In any case, the reason this is great for us is if there's symmetry, I can find the electric field sort of just by using arguments of geometry, by calculating the area and figuring out what the angle is. I can calculate E. If I know all the charges inside some closed surface, boom, I can find E so long as I stick to something symmetric. So let's go back to our hollow charge of sphere again. So I've still got that darker blue sphere that's the racquetball, and I've kind of drawn inside it an imaginary sphere that's light blue. Now this isn't something that really exists. It's what mathematicians and physicists call a Gaussian surface. But it's a sphere that if I look at that sphere, I realize there's no charge inside it. I also recognize, because everything's symmetric with spherical symmetry, if there were charge inside of it, the electric field on the surface of that should be everywhere the same. There's no reason it's going to point more left or right or be stronger on the right side than the left side. So the electric field should be equal everywhere on that surface in magnitude and point outward. And since there's no charge inside that light blue sphere, there's no electric field on it. I mean, if I do phi on this, that q sub n is 0, so therefore EA cosine theta must be equal to 0. And the A is not 0, obviously, it's a sphere. The cosine is not 0 because the field would point straight outward, so therefore the E must be 0. If I go outside the sphere, now I've drawn my Gaussian surface, this light blue imaginary sphere outside it. And now I can see that the surface area of that sphere does have field lines that point through it. The field lines we talked about emerging from the surface of the racquetball, and they're everywhere perpendicular. They point straight outward, and they everywhere are the same magnitude. I mean, there's no reason this electric field is going to be stronger on one side than the other. So therefore, when I calculate the flux through this light blue imaginary sphere, it's going to be E times A times the cosine of theta. They're everywhere perpendicular, so the cosine of theta is equal to 1, theta is 0. And A is just the surface area of a sphere, 4 pi r. So therefore, E times 4 pi r squared is equal to Q sub n divided by epsilon naught, where Q sub n is whatever charge is inside that light blue ball. It's whatever charge I painted on the racquetball. Dividing through by the 4 pi r squared, what I get is E is equal to Q sub n divided by 4 pi epsilon naught r squared. And now this is why I've used epsilon naught, because you may remember that 1 over 4 pi epsilon naught in Coulomb's law was equal to K. So E is equal to KQ over R squared, which is just what we argued before, that if I'm out there on the surface of that light blue sphere, then the electric field is just the same as if the charge were exactly at the origin and had a magnitude of Q sub n, the amount of charge that's painted on the racquetball.